In our last lecture, we'll look at three more models that use exponential and logarithmic functions in them. Now, the first of these three is the Gaussian model, and these are the bell-shaped curves, or the curves that are normally distributed that we're probably used to seeing. Since these functions are rather complicated, and I'm sure we know a lot of statistics about normally distributed curves, we'll just talk about them briefly, and then we'll move on to more accessible models. So, if we look at the function for our bell-shaped curves, we see it's y is equal to a times e to the negative x minus b squared times 1 over c. And we have three constants that we can plug in for, a, b, and c. And any number we plug in for should give us a normally distributed curve that's either shifted right or left, and then stretched or shrunk, or whatever we want to do. Now, we're probably used to seeing a standard normal distribution, which uses the following equation: y is equal to 1 divided by the square root of 2 pi times e to the negative x squared divided by 2. And this is just a bell-shaped curve with very specific a, b's, and c's. A will always be 1 over 2 pi, b will always be 0, and c will always be 2. When we graph them down, they do take this nice bell-shaped curve on. And this is just any Gaussian model. It's not a standard normal distribution. But we say some things about any of these in general. And one thing in particular is when we say that it has an average value. So we say the function has an average value when x minus b is equal to 0, or x is equal to b. And if we look at the graph, we see that b is marked off as sort of the top of the bell-shaped curve, and it always gives us the maximum value for our Gaussian model. Now, what we're actually recording here with these values is the area under the curve. So when we look at these statistics and the probability, normally we're not just interested in finding what these values are, but we also want to find, we'll do blue here, how much of the area of the graph does an x value represent. And what's nice about these Gaussian models is that this midpoint, this b, is actually always going to be 50% of the graph. So it's the average value, and it also tells us where 50% of our data lies. So the lower 50% is to the left of b, and the higher 50% is to the right of b. Let's move on to another function now. And again, this one has ties to other fields, and in particular, this has ties to business and biology fields. And this is called the logistic growth model. Maybe let me scroll down just a little bit here so we can see the function. A logistic growth model initially has rapid growth, followed by a steady declining rate of growth as it sets towards some horizontal asymptote. Now, normally this is called either a logistic curve or a sigmoidal curve, and it models the growth of bacteria culture very well. As well, it models the growth of technology sales very well as well. Again, if we look at the equation, it is y is equal to some value a divided by 1 plus b to the power negative r times x. So a, b, and negative r are just constants that will fit whatever sort of culture or population or sale data that we're trying to match. And then x, as we scroll down a little bit more, normally represents time, and y either represents population size or how many sold. So if we look at this graph, what the initial curve before this dot represents, this very fast increase, is when the population's introduced and it starts reproducing like crazy. There's tons of resources, and so it's free to sort of roam around, and there's nothing getting in its way. However, as the population grows, the resources start to dwindle. And this black dot here represents where the population starts to have some stress. It can't reproduce infinitely. Eventually it'll reach a carrying capacity where the population can't grow any larger based on the size or the amount of material or food that is present. These functions normally reach a nice horizontal asymptote here that limit the total size of the population. Or again, if we're talking about technology sales, it sort of limits the maximum amount of sales possible, which maybe it'll grow past there a little bit, but we can always use the entire human population to be our horizontal asymptote, and we can never sell more products than that. If we talk about technology sales in particular, what this initial fast rise represents is when the new interesting technology comes out, like a new cell phone, and everybody wants it and they buy it up. However, once you buy a fancy, expensive cell phone, you're probably not going to buy another one of the same model just to have two. So sales start to dwindle once people have the phone, and eventually they reach some sort of selling cap, and we can use this data to find this rate of decline, this point where we're going to slow down our sales to figure out when we should introduce our next product and what that should be based on the total number of sales. The last of our 5 models is actually the logarithmic model, and it's very similar to our exponential growth and exponential decay, but notice that we have 2 different forms for our logarithmic model, and that's because we like to use base 10, as we see in y plus a, y equals a plus b times log of x. If no numbers given, it's always base 10. And we're also very interested in e, or natural logs, which we see in y is equal to a plus b times the natural log of x. And these come up quite frequently, not as frequently as exponential growth and exponential decay, but I'm sure you'll see them when you start looking at some data or you start looking at sales in general. And one thing that's easy to model with logarithmic models is the magnitude of earthquakes. And this is given by r is equal to log of I divided by I0, where r is the recording of the intensity of the earthquake. I is actually the max intensity at the epicenter, and I0 is the minimum intensity we record, and this is used for comparison. So unless I0 is specifically given, we usually just set it equal to 1 because we always measure this earthquake sort of dissipating out, so we can find it equal to 1 somewhere. Now let's see how this function works, and let's see why it's a rather surprising way to measure it, and how the Richter scale can really change as it goes up. Alright. So the first part of this problem, given a recording of 4.0 in Alaska, find the intensity of the earthquake at its epicenter. So r is equal to 4, and we have 4 is equal to log of I divided by 1. Since there was no I0 given, we'll assume it to be 1. And this is rather easy to solve. We simply undo the log and we move the base 10 to the other side. And we get that 10 to the power 4 is equal to I over 1, which is just I. At this point, we just need to find what 10 to the 4th power is, and we find that the intensity of the earthquake was 10,000 units. Okay, let's compare this against another earthquake. Given a recording of 6.3 in New Zealand, find the intensity of the earthquake, and we solve this in a very similar way. We have 6.3 is equal to log of I divided by 1, or in other words, 10 to the power 6.3 is equal to our intensity. And with the calculator, we find that I to the power 6.3 is very, very close to 2 million. So when we increase by about 2 on the Richter scale, we jump up a lot in the intensity of the earthquake. So note an increase of 2.3 on the Richter scale gives an increase of intensity by 2 million divided by 10,000, which is exactly 200 times stronger. So if you see an earthquake of 6.3, that's 200 times more intense than an earthquake of intensity 4, or of Richter scale 4. So these grow very, very quickly. And this is because if we think about our graphs of logarithms, they sort of lag as they increase. So the x value needs to really stretch out, or the intensity needs to get really, really far in order for the y value to go up much at all. And this is the end of this lecture. So when you think back on these, remember our few equations here. Remember our normal distribution. And we normally like to use this top equation, since we like to plug in a, b, and c as it fits the data. As well, I promise we'll see this logistic curve again. So remember that this is a nice model of bacteria or technology, and it's sort of this weird S shape of rapid growth and then rapid decline. And then finally, and most importantly, make sure you remember the two logarithmic models, because these are the most simple and they come up quite frequently.